So I figured what I would do is go over these chapter 17 and 18 practice questions that I made. I would say if I were going to give you an exam just on chapters 17 and 18, it probably would have looked something like this, although there's not very much material on that exam. Especially chapter 18 is pretty short. So the first question is treating this ketone with lithium aluminum hydride followed by an acid workup. Recall that lithium aluminum hydride will reduce pretty much any carbonyl compound. And I can even do this in one mouse click. It reduces C double bond O to HC single bond OH. So that would be the product. It leaves the carbon-carbon double bond alone. The next two are interesting and worthwhile studying. Their reactions will probably reference next semester also. We're treating the same ketoester with first lithium aluminum hydride and then sodium borohydride. As we went over in class, this will give two different outcomes. LAH will reduce both ketones and esters. It reduces the ketone to the secondary alcohol, and it reduces the ester all the way down to a primary alcohol. So LAH is the more reactive of the two hydride reagents. It reduces ketones, aldehydes, esters, and carboxylic acids. It reduces a ketone to a secondary alcohol and an aldehyde to a primary alcohol. And it will also reduce both carboxylic acids and esters to the corresponding primary alcohol. Again, primary meaning, forgot what word I just used. Corresponding meaning that it has the same number of carbons. So this carbon over here in the ester is this carbon over here. And the other parts of the ester, the oxygen winds up in the OH, and the ethoxy group winds up in a molecule of ethanol. And in class, we said that we ignore methanol and ethanol side products. Nearly all esters are ethyl and methyl esters. Oh, wait a minute. I am disobeying my own rules, I just realized. For full credit, you must show all applicable relative stereochemistry, but if the product is a racemic mixture, draw only one enantiomer. So this is a chiral carbon, so we need to show stereochemistry. This is a chiral carbon, so we need to show stereochemistry. And I could just as easily have done with a dotted bond. Either way is equally acceptable. They're both equally good answers, but we do have to show stereochemistry. Now, the next one, we're treating that same ketoester with sodium borohydride, and sodium borohydride will not touch carboxylic acids or esters. It will, however, reduce the ketone to the corresponding secondary alcohol. So sodium borohydride is a less reactive hydride reagent. And again, we've generated a chiral center, so we need to account for that in our answer. And that could have been a dotted bond or wedge bond. Either is equally good. The next one is a Grignard reaction, which I've already started reviewing for Organic 2, and we're going to talk about a little more, I believe, in chapter 19. And recall in class that we said that you attach the alkyl group of the Grignard reagent, whatever is attached to the magnesium gets attached to the carbonyl carbon, and you get a tertiary alcohol in this case from a ketone. I'm trying to think how best to draw this. struggling with ChemDraw tonight. And we want to draw one of the two enantiomers. There we go. That works. And I could have drawn the enantiomer also. Either way would be fine. So this carbon here is the CH2 in the ethyl Grignard reagent. And you get the tertiary alcohol. Now, on the other hand, if we started with an ester and treated with an excess of the Grignard reagent, and that could say either 2 of the Grignard reagent or excess of the Grignard reagent. They mean the same thing. Then, as we discussed in class, you get a tertiary alcohol in which both of the alkyl groups attached to the magnesium, it doesn't have to be ethyl. So if I give this on the exam, it may not be ethyl Grignard. It might be a different Grignard reagent. So don't just memorize it CH3CH2. It could be any alkyl group on the Grignard. And whatever the alkyl group is, you put 2 of them on what used to be the carbonyl carbon, and you change C double bond O to C single bond OH. And now this carbon is not chiral. So there's no wedges and dots. It is 2 of the same group on it, so it's not chiral. Good. I can't think of anything else. That's about it for the first page. Questions so far? So the next question has to do with protecting alcohols. And we said in class that one way to protect alcohols is by treating them with a chlorosilane. And what happens is instead of the OH bond, you get an oxygen-silicon bond. You remove the chlorine from the silicon, and whatever alkyl groups are attached to the silicon remain attached. And then you also need either triethylamine or pyridine. Either one of the two will work just fine, but you do need a base to pick up the HCl. Whoops. So you would get this silyl ether. Whatever alkyl groups are in the silicon, just go along for the ride. And this you could now make into a Grignard reagent. You could make it into an alkyl lithium. You could make it into a cuprate. You could make it into anything that has a metal in it. And now the alcohol is protected. It's covered so that we don't need to worry about the presence of a protic functional group that would prevent you getting, you can't make a Grignard reagent from this. You can make a Grignard reagent from this. If you treated this compound with magnesium, you would get the Grignard reagent. So if you treated this with magnesium in either diethyl ether or THF, either of the two would be suitable solvents. You want an ether solvent for making a Grignard reagent. You certainly don't want anything protic. Anything protic will prevent you from getting the Grignard reagent. And I believe in Organic Chemistry 2 lab, you will make a Grignard reagent. So you'll actually get to experience it. It's pretty cool. Whereas if you treated this one with magnesium and diethyl ether or THF, you wouldn't get a reaction. You just get a lot of white sludge, a bunch of magnesium salts. But you wouldn't be able to get a Grignard reagent because Grignard reagents are protonated by protic species such as alcohols and carboxylic acids. That's good review for the final from chapter 10, I think it is. So be aware that you can't have any protic groups, and we defined the word protic in chapter 11. So you can't have any protic groups in the presence of a metal. Well, presence of most metals. All of the metals that we discussed this semester. Good. And this is an example of a compound that we might get from this Grignard reagent. In fact, if you treated that Grignard reagent with benzaldehyde, that's a benzene ring with an aldehyde functional group on it. CHO means aldehyde group, followed by dilute aqueous acid workup. That's exactly the compound you would get. So this is good practice for synthesis problems also. Anyway, once you add this compound, if you treat a silyl ether with fluoride, we mentioned this in class, the fluorine will take off the silicon because silicon and fluorine make an extremely strong bond. And you get the alcohol back. You deprotect the alcohol. So what you need to know is that on treating a silyl ether with a fluoride salt, could be potassium or sodium fluoride, doesn't matter which fluoride salt. In the presence of a protic solvent like water, you will get the alcohol back. And you'll get triethyl fluorosilane. So that's another chapter 17 reaction. In fact, it looks like all of the reactions so far are chapter 17 reactions. Looks like I went pretty much in the same order as the class. We also talked about phosphorus oxychloride in class. It needs a base such as pyridine or triethylamine in order to work. And this will do a dehydration reaction. So you take away the OH and an adjacent H, and you get a carbon-carbon double bond. So that's the H and the OH that you take away in order to make a double bond. The next reaction is an oxidation reaction using Dess-Martin periodinane. Dess-Martin periodinane will oxidize a primary alcohol to an aldehyde and a secondary alcohol like this one to a ketone. And the solvent is dichloromethane. And you'll notice I took away the wedge bond. Actually, the program did it automatically because now this carbon is not chiral. It's sp2 hybridized. So there's no wedges or dots. It's not a chiral compound. That's a very important thing to know from chapter 5, is how to tell when a compound is chiral or not. That's going to be important all next semester as well. Good, and the next one is a Fischer esterification reaction. We won't learn the mechanism until chapter 21, but we said that the OH group of the carboxylic acid and the alkoxy group of the alcohol, whatever the alcohol might be, whatever the alkoxy group is, by alkoxy I mean alcohol minus H. Alcohol minus H equals alkoxy group. You just attach the alkoxy group of the alcohol in place of the OH group of the carboxylic acid. So you would get, in this case, the ethyl ester, plus a molecule of water. And that's basically it. Questions on any of those 5? I'm just making sure I didn't make any mistakes. Good. So in the next one, we're treating dibutyl ether with 1 equivalent of HCl. And we went over that mechanism in class, and we showed how you get 1 molecule of an alkyl halide and 1 molecule of an alcohol. But we cleave 1 of the carbon-oxygen ether bonds. And the carbon side gets a halogen attached, whatever the halogen is in the hydrohalic acid, and the oxygen gets an H attached. And we went over the mechanism. Time seems to be going very slowly, so I might as well do the mechanism. First, let's figure out what the products look like. From the left side of the molecule, we get 1 chlorobutane. And from the right side of the molecule, we get 1 butanol. So those are the 2 molecules we'll get. The mechanism of the reaction goes by protonating the ether oxygen using whatever the hydrogen halide is. So in the next intermediate, the ether is protonated. And you get this intermediate. And this will now react with chloride. Now we have to think, is this going to react in an SN1 fashion or in an SN2 fashion? The way you know that is by looking at the group that's attached to O. Is that group primary or is it tertiary? If that group is primary, remember primary substrates do not form carbocations readily. So it's going to react by an SN2 reaction. If this group were instead tertiary, then it would go by an SN1 reaction. And we did an example like that in class, I'm quite sure. Secondary substrates can go either way. Either would be correct. But since this goes by an SN2 reaction, it goes by chloride attacking that carbon that has the OH on it. And both of those happen at the same time. This is an SN2 reaction because it's primary. The group is primary. And as you can see, it doesn't matter which side we attack on. The ether is symmetrical. And that gets you to those two compounds. Over here, you get one chlorobutane, and over here, you get one butanol.
Real quick, can you repeat what you called primary?
I'm trying to circle it. This group here is what's primary. And the way you know it's primary is because it is a CH2 attached to the oxygen. The CH2 makes it primary. Falls into the definition of primary. Is that what you meant?
Yeah. I just got confused. It looks secondary.
Well, this group on the side is primary. It's what I've circled that matters. We're not looking at groups at the same time. We can only lose one at a time.
Oh, okay. Thank you.
Actually, that was a good question. I probably didn't explain that very well. Good. This one, I want to go over the mechanism too. So in the first step, we treat the alcohol with sodium amide, which is a very strong base. So you need to know that's a very strong base. It's the conjugate base of ammonia. And that pulls off the proton from the alcohol and makes O-. Then O- acts as a nucleophile and attacks the primary alkyl halide and does a Williamson ether synthesis, which is nothing other than an SN2 reaction. And in the end, you get an ether. And this carbon here is the CH2 in the benzyl bromide. The CH2 right over here. So let's review that mechanism as well. I don't think I've ever had an organic 1 class that wanted to see the mechanisms more than this one. So that's NaNH2. Remember, in the mechanism, we don't even show the sodium. And this will pull the proton off the alcohol. This is all in chapter 18, by the way. So you get O minus where there had been OH. That now does an SN2 reaction on benzyl bromide. And you get the ether. Of course, the way the question's phrased, you don't have to show the mechanism. I just want to prove to you that this is the product that you get. Let's see if I can do this. Yes, it worked. Wait. I really shouldn't have used the exact same compound as I used in class. But in this case, we do an epoxide ring opening. And unless I've done something wrong, that's the compound that you get. Should have 7 carbons besides the ethoxy group. 1 and 6 make 7. 1 and 6 make 7. So the ethoxide attacks the less hindered carbon. And we'll do the mechanism. Attacks the less hindered carbon, less substituted carbon. Because it's an anion, we're in alkaline or basic conditions. And that was one of the things we said about alkaline ring opening of an epoxide. So the ethoxide attacks the less hindered carbon, the less substituted carbon, because there's more room there. And breaks the epoxide ring. And you get this alkoxide intermediate. The alkoxide intermediate then just needs a proton in order to give a neutral product. And so we look at what we're given. We're given sodium ethoxide and ethanol. Ethanol is protic, so we can get a proton from an ethanol molecule. And that's exactly what we do. And that then gives you the product. So that's how ring opening of epoxides looks in alkaline conditions. Make sense? The next one is ring opening of an epoxide under acidic conditions. And the way you know it's acidic is because there's an acid present. It's the conjugate acid of ethanol. This could also be written as ETOH and H2SO4. The H2SO4 is a strong acid and will protonate a few molecules of the ethanol and give the conjugate acid of the ethanol. So that could be written either way. And in acidic medium, ring opening of epoxides happens by attack of the alcohol on the more hindered carbon, because there's more of a buildup of a plus charge there. And you'll see that when we do the mechanism. So that's the product that you'd get. Since we're an acidic medium, we need to start by protonating the epoxide oxygen. And by the way, what I just drew is ETOH2+. That's the same thing. I just drew out the structure so you could see where the proton was. So you'll just use whatever species it is that you're given as your acid. So that's the intermediate that you get. And now your alcohol attacks at the more hindered position. You'll notice here I'm using the alcohol that I'm given. This is the solvent of the reaction. I'm not using ethoxide. You can't have ethoxide in acidic medium. It's really important to be able to discern whether you're in acidic medium or alkaline medium. And the way you do it is based on the species that you're given. If you're given an acid, then you're in acidic medium. If you're given an anion, which could be given you as a sodium or potassium salt of an anion, then you're in alkaline medium. Just to review what we went over in class. And now the alcohol will attack in the more hindered position. Because there's more of a buildup of plus charge there. I'm helping the oxygen to bear the plus charge. Right? Because the more substituted carbons make more stable carbocations. So more substituted carbons like the plus charge more than less substituted carbons. Both of these carbon atoms in the epoxide are helping the oxygen to bear the plus charge. But the more substituted carbon more so. Because more substituted carbons make more stable carbocations, and so more substituted carbons can bear plus charge better than less substituted carbons. So you get this intermediate. And now all we need to do is pull the proton off that oxygen to get rid of the plus charge. And we'll simply use the solvent that we're given. The solvent we're given is ethanol. And that then goes on to the oxygen with a plus charge. And you get the product. So ring opening of epoxides has different outcomes depending on whether you're in alkaline condition or in acidic condition, or alkaline solution or acidic solution. And this reaction is just a simple SN2 reaction. Of HS minus attacking the carbon that has the leaving group on it. Please do remember for reviewing chapter 11, not all leaving groups are Br. This one happens to be, but there are other leaving groups too. Chloride and iodide are also good leaving groups, as is tosylate. And we defined and drew the tosylate in chapter 11, and we also reviewed that, let me see, in chapter 17. So be sure that you're familiar with tosylates, because tosylate is also a good leaving group. And we defined that and drew it all in chapter 11. But the reaction is just an SN2 reaction. It all happens in one step. And you get the thiol plus sodium bromide. Good. Questions in either of those two? So let's do these mechanisms. This is the reaction of an alcohol with phosphorus tribromide to give the inverted alkyl bromide. And whatever stereochemistry you started with, you get the opposite stereochemistry of the bromide. That's because an SN2 step happens in the mechanism. That's the structure of phosphorus tribromide. And the alcohol oxygen attacks that phosphorus. The phosphorus is very electron deficient, very low on electron density because it has 3 electronegative bromine atoms attached to it. And the phosphorus bromine bond is pretty weak. So this is kind of like an SN2 reaction also. I'll even put SN2. And you get a phosphorus with 2 bromines attached to the oxygen. This is the new bond we just formed between oxygen and phosphorus. Oxygen and phosphorus, as we'll learn next semester, form really strong bonds. Oxygen and phosphorus really like each other. And next, what happens I don't know why it's not letting me draw these. There we go. So next, what happens is a bromide ion attacks the carbon that bears the oxygen and breaks the carbon-oxygen bond. And that entire group leaves, HOPBr2. The entire thing leaves. The reason it's a good leaving group is because the oxygen is a plus charge on it. So that's a very good leaving group. Good enough even for bromide, which isn't the greatest nucleophile in the world. To kick out the leaving group. And that gives the product. The bromide ion comes from behind. So where this is a wedge bond to the oxygen, the bromide comes from behind it and kicks out the leaving group. And so the new carbon-bromine bond is from the back. So we have a dotted bond. And the other piece is just HOPBr2. It's inorganic. So the major organic product is this alkyl bromide. And this is also an SN2 reaction. So pretty straightforward, just 2 steps.
Just real quick, since the Br comes from the back, that's why it's a wedge bond.
Dotted bond, yes.
Or yeah, dotted bond.
Yes, it's because it comes from the opposite side of the carbon-oxygen bond.
Okay. Oh, and it's SN2 that changes the
Yeah, it's
stereochemistry.
SN2, and that changes the stereochemistry. Yep.
Okay, thank you.
And we're going to find the very same thing happens with the next reaction. Here we're treating the same alcohol with thionyl chloride in pyridine in order to give the alkyl chloride, which is again inverted. And that's because there's again an SN2 reaction. So we need to draw thionyl chloride. That's the structure of SOCl2. The first step is the oxygen attacking the sulfur. And we break one of the sulfur chlorine bonds. And you get this intermediate. And then since we have a base present, we have pyridine present, Pyridine pulls the proton off of that intermediate to make a neutral product. So the nitrogen of the pyridine pulls off the proton. We break the hydrogen-oxygen bond. And you get this intermediate. And that's the intermediate that the chloride ion attacks. So the reason that this is such a good leaving group is because we make a molecule of SO2 that part of the molecule makes SO2. Ooh, I forgot my lone pairs on sulfur in both cases. That's better. The sulfur does need to have a lone pair to be correct. And the chloride again comes in from the back. This is an SN2 reaction. And really, this first step is kind of like an SN2 reaction also. And that gives us the product directly. You also get SO2 and another chloride ion. You use up a chloride ion and you make a chloride ion. So we're even in chloride ions from that step.
Real quick, would the sulfur have a formal charge other than 0?
No, the sulfur remains at 0. And thionyl chloride at 0. And I think if you plug into that formula, it will come out 0. Remember, sulfur can have more than 8 electrons around it. All of your elements in the third row of the periodic table and below can become hypervalent. They don't have to be, but they can be. So none of the sulfurs should have a charge.
Okay, thank you.
Good question, though. Next, we'll practice some more epoxide ring openings. The first one is under alkaline conditions because we have an anion. Remember that Grignard reagents act like carbanions. And the carbanion is a C with a minus charge. So it acts like this carbon here has a minus charge. And so we form a new bond between this carbon and that epoxide carbon. That's what that arrow signifies. And we also break the epoxide open. And that releases all that ring strain. And this carbon is this carbon. And you'll notice that carbon is not involved in that mechanistic step. So the bond to oxygen remains wedged. There's no SN2 reaction or anything happening on that step. So that's what you get after adding the Grignard reagent to the epoxide. Then in a second subsequent step, we add dilute aqueous acid. The first thing the acid will do is protonate any leftover Grignard reagent. You probably used a slight excess to make sure that you consumed all of the epoxide. And so that's the first thing that will happen. And then the hydronium ion puts a proton onto the O-, onto the alkoxide ion. So in the next step, we just draw the hydronium and we show it protonating the O-. And that gives us the product. Only 2 steps. This first step is an SN2 reaction, but the carbon that gets attacked is not chiral. It's a CH2, so there's no stereochemical outcome. In the next one, we have an epoxide ring opening under acidic conditions. And remember, the first thing we do in acidic conditions is protonate the oxygen. And the reason that we protonate the oxygen is because we can't just have a nucleophile attack the carbon, because if we did, then we would get an oxygen with a minus charge. And you can't have an oxygen with a minus charge in acidic solution. It's too alkaline. It would be protonated immediately. So there's your CH3OH2 plus. This will protonate the epoxide oxygen. A question I get a lot during exams is if it's okay to use the structure that you're given without redrawing it fully. And the answer is, if you can show the mechanism clearly, then certainly you can. All I needed to do was add the lone pairs on oxygen. And that saved me the trouble of redrawing it. So that's the intermediate that you get. Next, you take whatever alcohol you're given. In this case, it's methanol. It will probably be an alcohol or water. But whatever the solvent is, you take that, and now we attack again on the more substituted carbon, because that carbon helps the oxygen bear more of the plus charge. And then you get this intermediate. And then all we need to do is pull that proton off the oxygen with a plus charge, and we're done. So the question then becomes, what do we use to pull the proton off? And the answer is we need to look at what we're given. We're given methanol and the conjugate acid of methanol. Of those two species, methanol is more alkaline. You need to use what you're given in order to decide when you're about to use something as a base or an acid. You need to use what you're given. So we use the methanol to pull the proton off of that oxygen and get rid of the plus charge. And then we get the product. I should also have mentioned that this step here is SN2. That's why we have inversion of configuration. This carbon here is this carbon over here. And this oxygen is this oxygen. So that's how the mechanism looks in acidic medium. Good. And that's pretty much it for that document. We have 25 minutes left. I know everyone wants to ask, is this going to be on the exam? Is that going to be on the exam? I really can't answer questions like that. Everything is fair game from the whole semester. But this was a good review of chapters 17 and 18. I think we covered just about every reaction that was in those two chapters. Pretty close anyway. I thought what we might do with the time left is practice some synthesis. Unless anyone has a question, if there's something in particular you'd like me to give an example of and go over, I can do that. Let's see.
Just as a question at the end, if you could go over cis dihydroxylation, but with if it's a
Ah,
carbonyl or a ketone, like the differences.
cis dihydroxylation. Well,
Yes.
but that's a reaction of alkenes. You shouldn't get a ketone.
Oh, sorry. It's I think it was on the homework or something. It's H2ErO4. And it adds oxygens in different places if it's carb. No, it changes an alcohol to a double bond O on carbonyls and ketones in a different manner. I'll look up what it's actually called.
Yeah, I don't recognize the reagent. You're saying it's an oxidizing agent. It oxidizes alcohols to carbonyls. Oh,
Yes.
H2CrO4. Yes. I thought you said H2BrO4. Yeah, I talked about that in class because it is on the homework, and thus is fair game. This can also be written as CrO3. It's the same thing. H2CrO4 is what you get when you take CrO3 and add H2O. You get H2CrO4. This is an equivalent reagent to KMNO4. They do the same thing. So it oxidizes a primary alcohol to a carboxylic acid. And it oxidizes a secondary alcohol to a ketone. And that's basically it. Both of those reagents oxidize a primary alcohol to a carboxylic acid and a secondary alcohol to a ketone. And you're not responsible for the mechanism.
Okay, thank you.
Sure. So let's practice some synthesis. And there's nothing special about the 3 arrows. I got a lot of questions about that. The idea is to turn this compound into this compound. So first thing we do is count carbons. This compound has 5 carbons. And this compound has 10 carbons. So somehow we've taken 2 of these compounds and connected them at this carbon. That means we need to convert the alkene to something that has an atom there that we can connect to another group. And I think the easiest way to do that Why is it doing that? The easiest way to do that is to treat that alkene with HCl, HBr, or HI. And that puts a functional group in that position that we can then use in order to form this new carbon-carbon bond. Now, in chapter 10, we said that one of the best reactions for forming new carbon-carbon single bonds like this is the Gilman reagent, or the cuprate. So remember, you can work both forwards and backwards in synthesis problems. That means that if we had this bromide, and we had this cuprate, we could react them together and they would give this compound. So we would need to react that cuprate with this bromide, and it would connect this carbon to this carbon. So you can look up that reaction in chapter 10. So the only question, we already have this bromide. We've made it by adding HBr. And true, you could also do, let's say, oxymercuration, followed by converting the alcohol to the bromide with PBr3, but why bother when you can make the bromide directly? It would be acceptable, though. It just has an extra step that's not necessary. But it would absolutely be acceptable. With synthesis problems, there's often multiple correct answers. And one thing I've noticed with grading synthesis problems is it seems someone always comes up with something that I never would have thought of, but works, so I accept it. So there's often multiple correct answers. So then all we need to do is remember how to make the cuprate. And the way you do that is you take some of this bromide and you first add lithium. That's also a chapter 10 reaction. And that gives you the alkyl lithium. And then you treat the alkyl lithium with copper 1 iodide. And you get the cuprate plus lithium iodide. So the full synthesis would be treating the 1-pentene with HBr to give 2-bromopentane, taking some of the 2-bromopentane and making the alkyl lithium by treating it with lithium metal and pentane, then converting the alkyl lithium to the cuprate, and finally treating the cuprate with some more of this alkyl halide that we made, and that will give you this compound. It will form that carbon-carbon bond. between the two 5-carbon chains. Something like that, I think, is the best way to do it. But there might certainly be other ways. And really, this whole worksheet is a good review of cuprates. The syntheses use material through chapter 10. So I don't think there's any chapter 17 or 18 material in these syntheses. Good, I think we have time for a couple more of these. Whoops. So 1, 2, 3, 4, 5, 6 carbons. And this one is 6 carbons. And I bet you anything this is 12 carbons, 6, 7, 8, 9, 10, 11, 12. So again, somehow we're adding these two pieces together. And it looks to me like we're connecting this carbon and this carbon somehow. And we can do that again with a cuprate. So the first thing we need to do is well, working backwards. And again, you can work from either end. We need to get those two bromides from this alcohol and this alkene. And once we do that, we can convert either of those two bromides to the alkyl lithium and then to the cuprate, just like we did before. This actually will be somewhat earlier in the synthesis. So can we make this bromide from this alcohol? Certainly we can. We went over that reaction in both chapter 10 and chapter 17. Phosphorus tribromide will convert a secondary alcohol to a secondary bromide in one step. That's no problem. And then we need to convert this alkene to this bromide. Notice that's the non-Markovnikov bromide. The bromine is on the less substituted carbon. So is there a way to do that in one step? Actually, there is, HBr and H2O2. But we didn't discuss that in class. It is in the book, but we didn't discuss it in class. The method we discussed in class is, first of all, making the non-Markovnikov alcohol by treating with borane and THF. Followed by aqueous alkaline hydrogen peroxide. That's a chapter 8 reaction. This is hydroboration oxidation. That converts the alkene to the non-Markovnikov alcohol. Then we can convert the alcohol, the primary alcohol, to the alkyl bromide the same way we did before. Phosphorus tribromide and diethyl ether. And that gives us that bromide, which we needed. So now we have both bromides. And you can write it just like this. This is fine. So now all we need to do is convert one of the bromides, it doesn't matter which one, to the alkyl lithium by treating with an excess of lithium metal and pentane. And then we turn that alkyl lithium into the cuprate by treating it with copper 1 iodide. That makes the cuprate. And then we treat the cuprate with this alkyl halide, and that gives the product. That forms a bond between this carbon and this carbon. And that new bond is right here. Wait, no, I'm sorry, right here. And there are other questions very similar to that on this page. I did also give the answer key.
Real quick, if the second compound, the cyclohexane with the alcohol, what if that was a tertiary alcohol? What would you have used?
I would have used HBr then to make the alkyl halide.
Oh, okay, thank you.
Yeah, tertiary alcohols, you're better off using the hydrogen halide. And my cat is still there. He hasn't budged. Well, we have 5 more minutes left. Let's do 2 of the easier ones. Let's do this one first. Here we're converting the carbon iodine bond to a carbon hydrogen bond. And I think the best way of doing that is by making an organometallic reagent from the iodide, either the Grignard reagent or the alkyl lithium, and then just treating it with water. In other words, if we had that Grignard reagent, and just treated it with water, the water would protonate the Grignard reagent. Just like that. And we can make that Grignard reagent just by treating the iodide with magnesium metal in either THF or diethyl ether solvent. Either ET2O or THF, take your pick. Either solvent is correct. So it's just two steps. Treat the iodide with magnesium, and then treat the Grignard reagent with water, or indeed any protic solvent. You could have used methanol, you could have used acetic acid, it doesn't matter, any protic solvent. And that will give you the alkane. We have a very similar question here, and this actually, we're going to use the reaction that you just asked about. We can form that alkane from this Grignard reagent by treating it with water. So if we can get that alcohol into a bromide, or indeed any alkyl halide, then we can just convert the halide to a Grignard reagent. I disobeyed my own rule and forgot to count the carbons both times. 1, 2, 3, 4, 5. And this one has 6 carbons, and the product also has 6 carbons. So we can get the Grignard reagent from the bromide by treating it with magnesium and diethyl ether or tetrahydrofuran. And then can we turn the alcohol into the bromide? We sure can. We would just treat it with HBr. And that will give the bromide plus water. Water will be the inorganic side product. So for synthesis problems, I'm afraid there is no substitute to really knowing all your reactions, backwards and forwards. It's key to being able to do synthesis problems. Whether they're in chapter 8, chapter 10, chapter 9, chapter 11, got to know them all. And that's 8 o'clock, so any last questions?
Just real quick, you said your, oh,
Sorry, I
sorry,
was just
your
saying,
office
give it a shot with my
hours.
back. I'm sorry.
Oh, yeah, he looks very comfortable. But for office hours tomorrow, you said that was from 1 to 2:30?
Yes, just as on a usual Thursday.
Okay,
I might
sounds
even
good.
be there a little early.
Okay, thank you.
Sure. All right. Well, I guess I'll see you all bright and early Monday morning. I wish you all the
Yeah.
best in the final.
Thank you, Professor. Have a good night.
You too.